we're going to look at some mathematical applications of differentiation now, and so sort of next week and beyond we'll be looking at some real life applications. But one mathematical application that you might have is to sort of understand whether a function is increasing at a certain point or whether it's decreasing at a certain point. So here we've got a very basic function. What we can do is very easily find f prime x, the gradient function. So it becomes minus 3x squared plus 6x, and the 5 will disappear. So we're trying to find the intervals where the following functions are increasing or decreasing. Well, a function is increasing if the gradient is bigger than 0. So all we're trying to do is find out when is this function bigger than 0. So that's the same as when 3x squared plus 6x is less than 0. Please remember that you'll never, ever, ever try to solve an inequality algebraically. You do it graphically. So we're going to just sketch this one. That becomes 3x upon x plus 2. So we've got 0 and negative 2 on my zeros. Okay, so when is this less than 0? It's when this would be 0, 0. This is negative 2, 0. It's when x is between 0 and minus 2, then the function is increasing. Okay? And by definition, when x is bigger than 0 or x is less than minus 2, then the function must be decreasing. Okay? Notice that not when they're equal to. When x is equal to 2 or when x is equal to 0, what we would say there is that the function is stationary. Stationary. That is to say that the gradient is 0 at those points. It is stationary. So the gradient is 0 at these points. Hopefully that makes sense. We can do the same with f dashed x. So we've got f dashed x equals, what's the gradient function here? That's going to be 12x cubed minus 24x squared, and the 2 will just simply disappear. Okay, so again, when is it increasing? When 12x cubed minus 24x squared is greater than 0. When is that gradient greater than 0? Well, factor out the 12 and an x squared, and we're going to get x minus 2. I think we've got the same answer really here. Well, have we? We're going to say when is that equal to 0? Now, that is a cubic, so let's just make sure we draw this properly. That means we've got one of those double roots at x is 0. And we've got a root at 2 as well. So something like this. It's going to be something like this. Okay? So now I've done it graphically. I can see when is my function bigger than 0? Well, it only tends to be when x is greater than 2. And so logically, when x is less than 2, we have, this is increasing function, and this is a decreasing function. Okay? At x equals 2, we have a stationary function. But also at x equals 0, we have a stationary function. Okay, might seem weird, how can that be the case at 2 different points? But hopefully that will become clearer in a minute. If you wanted to just check that, do it yourself. I'm not going to do it. Put these functions into Desmos and have a look and check that we're right. So, for example, check with this one that my gradient is increasing when x is bigger than 2, decreasing when x is less than 2, and it's 0 at x is 2 and x is 0. And then you might sort of understand how that can happen with both, okay? Right, let's just carry on. Right, so another application, and very much linked to what we've just been doing, we can find turning points in functions. We can find maximums and minimums, okay? So here we've got a function. It'll be very clear that this function is limited to the domain -5 to 6, okay? I don't know what the function is, probably some cubic, but it's cut off between -5 and 6, okay? Now, what I want to understand is what we've got here is we've got a global minimum point. This is the lowest y value on the function. And here we've got a global maximum point. This is the highest y value on the function. But here is what we call a local maximum. A local maximum. And here we've got a local minimum. Okay, so don't get the two confused, all right? Now, differentiation can help us find local maximums and minimums. As you can't really help us find global maximums and minimums. Sometimes they're the same thing. Depends on what the graph looks like, okay? But differentiation only helps us find these local maximums and minimums. And what it can also do is help us find what are called points of inflection. They're just points of inflection are where the gradient approaches 0, but rather than turning around, it then sort of carries on to basically what you've got is a positive gradient turning into a 0 gradient and then back into a positive gradient. As opposed to at a local maximum, we've got a positive gradient that goes 0 and then turns negative, and a local minimum where it's negative turns 0 and then goes positive. And of course, a point of inflection could be the opposite. We could have a negative gradient that goes to 0 and then goes back to being 0. So these are points of inflection, okay? So all of these are called stationary points. Stationary points, right? Very, very important language. And these are points at which the gradient is equal to 0. So we've got maximum, local maximums, local minimums, and points of inflection. Inflection, okay? Might be worth noting as well that a point can be a point of inflection, but it may not be a stationary point, okay? A stationary point can be a point of inflection, but a point of inflection is not necessarily a stationary point, okay? For example, if I did something like this, this would be an inflection point, but the gradient is not 0. It's simply the point at which the gradient itself is, here the gradient is getting shallower and shallower, and then at this point it suddenly starts to get steeper and steeper. So it's sort of where it changes. Okay, that's what the point of inflection. It might not have to go all the way to 0 for it to be considered a point of inflection. So a point of inflection might be a stationary point. It might not be a stationary point. Okay. Now, hopefully this will become clearer as we go through. Right, now, what you might be asked to do is work out the nature of a stationary point. So if you're asked that question, the nature of a stationary point, what you're essentially being asked is what type of stationary point do you have? Do you have a maximum? Do you have a minimum? Or do you have a point of inflection? Okay. In order to know this, what you need to understand is that derivatives can keep going. So you've seen that you've got a function f of x. Let's say it's x to the power of 4, and we can find the gradient function, which would be 4x cubed. What we can do is we can find a second derivative, f dash dash x is what we call it, and that would be 12x squared. We can even carry on. We can go for the third derivative, f prime 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 x, okay, and that would be 24x. Sometimes you use this notation if I want to go to the fourth derivative, Okay, I can just use the number, and that would be 24. And then the fifth derivative, finally, would be 0. Okay, so we can actually go as much as we like. The notation, if you're going to use Newtonian, it goes y, it goes dy dx, it goes d squared y dx squared, d cubed y dx cubed, so on and so forth. And you can really do as many as the function actually allows you to do. So we've got fn x, and we've got dny dx n is the notation for the nth derivative of a function. Now, you know, not all functions have infinitely many derivatives. Some functions you can have infinitely many derivatives, and some just have a fixed amount. Polynomials have a fixed amount, depends on the order of it. Okay. So let's carry on. Now, why is this helpful? What we can do is what we find out is if we pick a point, a stationary point, then if the second derivative at that point is less than or equal to 0, then we have a maximum. I'm not going to explain why. I would like you to try and understand why, okay, by playing with it. If the second derivative at a certain point, at a certain stationary point, is that should be less than 0, not equal to, is greater than 0, then we have a minimum. If the second derivative at a stationary point is equal to 0, you might think it's a point of inflection, but actually we don't know. We don't know. And then we have to do another method, which I'm going to teach you live rather than on the video, okay? So it might be a maximum, it might be a minimum, it might be a point of inflection. It can only be a point of inflection if the second derivative is 0. But it might not be, okay? Might be a maximum, might be a minimum. We simply don't know. So let's have a look at this. We've got a function here, and what we want to do is find out where the stationary points are first, and then what are the nature of those stationary points. So the first thing I'm going to do is I'm going to find the first derivative, which is going to be 3x squared minus 6x minus 9. Now, when do I get stationary points? Stationary points happen when the gradient is equal to 0. Okay, the tangent at a stationary point is 0. So I'm saying, when is this equal to 0? Divide everything by 3, x squared minus 2x minus 3 equals 0. So I'm getting x minus 3 and x plus 1 equals 0. So I'm getting stationary points at x equals 3 and at x equals negative 1. So there are two stationary points on this curve. Hopefully not surprising because it is a cubic. So that's what we're going to get. So I know where the stationary points are. Of course, I can now work out what the y value is at those stationary points by subbing in, you know, if I find f of 3, then I know what the y value is at that stationary point. I'm not going to bother with that. What I want to know now is what the nature of these stationary points are. So what I need for that is the second derivative, which is just the derivative of the derivative. Okay, it's going to be 6x minus 6. So now what I'm going to do is I'm going to look at what is the value of the derivative at that x point. So f dash dash 3 is equal to 18 minus 6, that's equal to 12. And the beauty of it is I know that this is greater than 0, therefore this is a minimum. Okay? So I've got a minimum of x equals 3. And I can do the same for f prime prime of negative 1. So sub that into the second derivative, I'm going to get minus 6 equals negative 12, which is less than 0. Therefore, this is a maximum. Okay? So I've got two stationary points. Let me just sketch it. Okay, one stationary point at negative 1 something, I'd sub that in. I'd find f of -1. Who knows what it is? It's probably maybe somewhere like here, okay? And then at x is 3, I have a minimum, okay? Maybe my y value is about there, don't know. So I have a maximum, I have a minimum, hang on, I've done something crazy here. Have it, maximum, minimum, how can I've made a mistake here. Must have done. At x equals 3, I've somehow managed to get myself, that's right, okay. That's why it will look like this. Okay, a minimum at x. No, hang on. I've totally confused myself here. Doesn't make any sense. Have I done that right? Sorry guys, just bear with me a second. If it's greater than 0, I get a minimum. If it's less than 0, I get a maximum. Right, guys, I've confused myself. So in order to not lose what I've done, I'm going to stop the video there and I'm going to figure it out and go back to part, come in the next part.